Right now, somewhere in this galaxy, a planet that spent billions of years in a perfectly stable orbit is being destroyed. Not by an asteroid, not by a collision with another world. It's being killed by its own star. The star it orbited faithfully for eons has begun to die, and as it dies, it's expanding, swelling outward like a balloon inflating in slow motion, and it's swallowing everything in its path. The planet's atmosphere is being ripped away, molecule by molecule. Its oceans, if it ever had them, boiled off long ago. Its surface is melting. And the worst part is, this isn't rare. This happens to planets all over the universe, and one day, billions of years from now, it's going to happen right here in our own solar system. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you probably take for granted. The stability of a star. Because that stability is everything. It's the reason you exist. It's the reason Earth has oceans, and an atmosphere and a comfortable temperature that allows you to walk outside without being incinerated or frozen solid. It's the reason life had billions of years to evolve from single cells into the complex conscious beings listening to these words right now. Your star defines your world. Everything about a planet, its temperature, its atmosphere, whether it can hold liquid water on its surface, whether it has any chance of supporting life, all of that is determined by the star it orbits. A planet without a star is a frozen rock drifting through darkness. A planet too close to a violent, unstable star is a scorched, irradiated wasteland. But a planet at just the right distance from a stable star, a star that burned steadily for billions of years without dramatic changes in its size or energy output, that planet has a chance. That planet can develop oceans. It can develop an atmosphere. It can develop life. Earth is one of those fortunate planets. Our sun has been burning steadily for about 4.5 billion years. In all that time, its energy output has increased slowly by roughly 30% since it first ignited. That sounds like a significant change, and over short timescales it would be. But spread across 4.5 billion years, it's an incredibly gradual shift. Slow enough that Earth's climate has been able to adjust. Slow enough that life has had time to adapt and evolve and diversify into millions of species. The sun today is remarkably similar to the sun that shone on the first single-celled organisms billions of years ago. It's a little brighter, a little larger, but fundamentally the same star doing the same thing it's always done. Fusing hydrogen in its core, radiating energy into space, providing a steady and reliable source of warmth and light to the planets that orbit it. But this stability is not permanent. It never was. Every star that has ever existed was born with an expiration date written into its physics. Stars do not burn forever. They run on fuel, and fuel runs out. When it does, the star begins to change, and everything around it changes too. Sometimes gradually, sometimes violently, but always irreversibly. To understand what happens when a star begins to die, you first need to understand what keeps a star alive in the first place. Because a star is not simply a ball of fire hanging in space, it's something far more extraordinary than that. A star is a nuclear furnace, deep in its core, under pressures and temperatures that are almost impossible for the human mind to comprehend. Atoms of hydrogen are being fused together to form helium. This process is called nuclear fusion, and it releases an enormous amount of energy. Every second, The Sun converts roughly 600 million tons of hydrogen into helium through fusion reactions, and in the process, about 4 million tons of matter are converted directly into pure energy, following the relationship between mass and energy that Einstein described. 4 million tons of matter transformed into energy every single second of every single day for 4.5 billion years. That energy radiates outward from the core, passes through the Sun's inner layers over the course of thousands of years, and eventually reaches the surface, where it streams out into space as light and heat. A tiny fraction of that energy, an almost negligibly small portion of the Sun's total output, reaches Earth, and that tiny fraction is everything. It powers every ecosystem on the planet. It drives the weather. It fuels photosynthesis. It keeps the oceans liquid and the atmosphere warm enough to support life. Without it, Earth would be a frozen, lifeless ball of rock and iron drifting in silence. But here's what's crucial to understand. The energy produced by fusion doesn't just provide light and heat to nearby planets. It also keeps the star itself from collapsing. A star is in a constant battle against its own gravity. Gravity is relentless. It's always trying to crush the star inward, pulling every single particle of gas toward the center. If gravity were the only force at work, the star would collapse into an incredibly dense point in a matter of minutes. The entire mass of the Sun would implode under its own weight. But the energy generated by fusion creates outward pressure, both radiation pressure from the photons streaming outward and thermal pressure from the superheated gas in the core. These outward forces push back against gravity, and for billions of years these two forces reach a balance. Gravity pulling inward, pressure pushing outward. Neither one wins, neither one loses. The star holds its shape, steady and stable in what astronomers call hydrostatic equilibrium. Think of it like a balloon. The air inside the balloon pushes outward against the walls. The elastic skin of the balloon pushes inward. The balloon maintains its shape because those two forces are balanced. If you pump more air in, the balloon expands. If air leaks out, the balloon contracts. A star works the same way, and for billions of years, this balance holds remarkably steady. The star sits on what astronomers call the main sequence, a long stable phase of life where it quietly fuses hydrogen into helium without any dramatic changes. The main sequence is where stars spend the vast majority of their lives. For a star like the Sun, the main sequence lasts about 10 billion years. More massive stars burn through their fuel much faster. A star 10 times the mass of the Sun might spend only 20 million years on the main sequence before running out of hydrogen. Less massive stars are the opposite. They burn their fuel so slowly that they can remain on the main sequence for trillions of years. Red dwarfs, the smallest and most common stars in the galaxy, are so miserly with their fuel that not a single one has ever died of old age in the entire history of the universe. The universe is only 13.8 billion years old. These tiny stars will keep burning for trillions of years more. But stars like the Sun, medium-sized stars with lifespans measured in billions of years, they eventually reach the end of their fuel supply. And when they do, the consequences are dramatic. In a star like the Sun, the dominant fusion process is called the proton-proton chain. This is the mechanism by which 4 hydrogen nuclei, which are essentially individual protons, are fused together through a series of intermediate steps to create one helium nucleus, which contains 2 protons and 2 neutrons. Along the way, particles called positrons and neutrinos are released, and a small amount of mass is converted into energy. The conditions required are staggering. The core sits at roughly 27 million degrees Fahrenheit, under pressure about 260 billion times Earth's surface atmosphere. Under these extremes, hydrogen nuclei overcome their natural electrical repulsion, merge together, and release energy. This process has been going on in the Sun's core for 4.5 billion years, and it will continue for roughly another 5 billion years. That sounds like an incomprehensibly long time, and it is by human standards. But it's not infinite. The Sun has a finite supply of hydrogen in its core, and it's consuming that hydrogen steadily, relentlessly, every second of every day, without pause. Now here's where things start to go wrong. As the Sun fuses hydrogen into helium, the helium accumulates in the core. Helium is heavier than hydrogen, and it settles toward the center. Over billions of years, the core gradually becomes enriched with helium, the byproduct of all that fusion. But here's the critical problem. The Sun's core, as hot and dense as it is not hot enough or dense enough to fuse helium. Helium nuclei have a stronger electrical charge than hydrogen nuclei, which means they repel each other more strongly. You need much higher temperatures to force them together. Roughly 180 million degrees Fahrenheit, compared to the 27 million degrees needed for hydrogen. So the helium just sits there. It accumulates. It builds up in the core year after year, billion after billion, like ash piling up in a fireplace that can never be cleaned out. And as that ash builds up, there's less room and less fuel for the hydrogen burning that's keeping the star alive. As the hydrogen in the core becomes depleted, the core's energy output begins to drop. And remember the balance we talked about. Gravity pulling inward, pressure pushing outward. When the energy output drops, the outward pressure decreases. Gravity begins to win. The core starts to contract, squeezed inward by the immense weight of the star's outer layers pressing down on it from above. But here's the counterintuitive part. As the core contracts, it actually gets hotter. This is a fundamental principle of physics. When you compress a gas, its temperature rises. The core of the star is being squeezed by gravity, and as it shrinks, it becomes denser and hotter. This increase in temperature has a dramatic consequence. The region just outside the core, a shell of hydrogen that was not previously hot enough or dense enough to undergo fusion, suddenly crosses the temperature threshold. Hydrogen fusion ignites in a shell surrounding the now helium-rich core. This shell burning, as astronomers call it, is actually more intense than the core burning that preceded it, producing much more energy. And that extra energy has to go somewhere. It floods outward into the star's envelope, the vast outer layers of gas that make up most of the star's volume. The outer layers respond by expanding. The star begins to swell, not quickly by human standards. This process unfolds over hundreds of millions of years, but by astronomical standards, it's remarkably fast. The star is leaving its stable main sequence life and entering a new and fundamentally different phase of existence. It's becoming a subgiant, and eventually, a red giant. Let's walk through what this looks like for the Sun specifically, because it gives us the most intuitive and frankly, the most unsettling picture of what stellar death actually means. Right now, the Sun has a diameter of about 864,000 miles. It's a steady, reliable presence in the sky, sitting about 93 million miles from Earth. But around 5 billion years from now, the Sun's core will have converted most of its hydrogen into helium. the core will contract, shell burning will ignite, and the sun will begin to expand. At first, the changes will be subtle. The sun will slowly brighten and grow slightly larger over hundreds of millions of years. It will pass through a subgiant phase where it's noticeably larger and more luminous than today, but still recognizably the same star. But then, the expansion accelerates. The sun will eventually become a full red giant. Its outer layers will balloon outward to staggering dimensions. The sun's diameter will grow to somewhere between 100 and 200 times its current size. As a red giant, it could swell to more than 150 million miles across. To put that in perspective, that's roughly the current distance from the sun to Earth. The sun will become so large that its surface will extend to approximately where Earth's orbit is right now. If you could somehow stand at the distance of Mars and look back toward the inner solar system, you would see an enormous red sphere filling the sky, where a modest yellow star used to be. The luminosity will increase dramatically. The sun as a red giant will be somewhere between 1,000 and several thousand times more luminous than it is today. That's not a subtle brightening. It's a transformation so extreme that a time traveler visiting this future solar system would not recognize the sun as the same star. Instead of a bright yellow disk in the sky, they would see a bloated, glowing red orb radiating vastly more energy in every direction. The surface temperature, however, actually drops. This might seem like a contradiction. How can a star producing vastly more energy have a cooler surface? The answer lies in the geometry. The sun, as a red giant, has a surface area thousands of times greater than its current surface area. Even though the total energy output is enormously higher, that energy is being spread across a vastly larger surface. Each individual square mile of the surface emits less energy than it does today. The surface cools from its current temperature of about 10,000 degrees Fahrenheit to roughly 6,000 or 7,000 degrees Fahrenheit. This lower surface temperature gives red giants their distinctive color. They glow red and orange instead of yellow and white, because cooler surfaces emit more long wavelength light. But do not let the word cooler mislead you. The star is still enormously hot, and the total energy flooding into the surrounding space is vastly greater than anything the nearby planets have ever experienced in their entire history. One of the most dramatic moments in this process is something called the helium flash. Remember that helium core building up in the center of the sun for billions of years? As the core contracts and heats during the red giant phase, it eventually reaches about 180 million degrees Fahrenheit. At this temperature, helium can finally begin to fuse, slamming together to form carbon and oxygen. But in a star like the sun, this ignition happens under special conditions. The core has become so dense that it exists in a state called electron degeneracy, where quantum mechanical effects prevent the gas from expanding normally in response to temperature increases. When helium fusion ignites under these conditions, the core cannot expand to regulate the reaction. The temperature spikes violently. The fusion rate skyrockets. In a matter of seconds, the core releases an enormous burst of energy. This is the helium flash. Despite its ferocity, the helium flash doesn't destroy the star. The energy is absorbed by the overlying layers before it reaches the surface. But internally, the flash lifts the degeneracy. The core expands, cools slightly, and settles into a new stable phase of steady helium fusion. The star contracts somewhat and enters a brief period of relative stability fusing helium in its core and hydrogen in a shell around it. But this calm is temporary. The helium runs out too. The core contracts once more. A helium-burning shell ignites around the now carbon and oxygen core, and the star enters what astronomers call the asymptotic giant branch phase, swelling even larger and becoming deeply unstable. It undergoes thermal pulses, periodic surges in energy output that cause it to brighten and dim in cycles. The outer layers become loosely bound. Intense stellar winds blast material off the surface, and the star begins shedding its outer layers into space, creating a glowing shell of gas called a planetary nebula. Over tens of thousands of years, the star loses a significant fraction of its total mass through these winds. What remains after the outer layers are gone is the exposed core, a dense, incredibly hot object, roughly the size of Earth, but containing about half the mass of the original star. This is a white dwarf. It no longer produces energy through fusion. It's simply cooling, radiating its stored heat into the void over trillions of years, slowly fading toward darkness. This entire journey, from the end of stable hydrogen burning through the red giant phase, the helium flash, the asymptotic giant branch, and the planetary nebula, takes several 100 million years for a star like the Sun. That's a long time by human reckoning, but it's brief compared to the billions of years the star spent calmly burning hydrogen on the main sequence. The Sun will spend about 10 billion years in stable equilibrium. The dying process will take only a fraction of that. It's like a person who lives a long, quiet life and then undergoes a dramatic transformation in their final years, becoming almost unrecognizable. And here's what matters most for our story. During this dying process, everything about the star changes. Its size increases by a factor of more than 100. Its luminosity increases by a factor of thousands. Its mass decreases as material is shed into space. The entire neighborhood of the star becomes a fundamentally different place than it was for billions of years before. For any planet orbiting close to that star, these changes are catastrophic. An orbit that was perfectly safe for billions of years, an orbit where liquid water could exist on the surface, where an atmosphere could be maintained, where life could emerge and thrive, that same orbit becomes as a death sentence. Not because the planet did anything wrong, not because the planet changed its position, but because the star changed around it. The anchor that held everything in balance for eons has become the destroyer. And this isn't some exotic or unusual scenario. This is the standard life cycle of most stars in the universe. Every star with a mass between roughly half the Sun's mass and about 8 times the Sun's mass will go through some version of this transformation. That includes the vast majority of stars that exist today. Somewhere in this galaxy tonight, a red giant is swelling outward towards a planet that orbited safely for billions of years. Somewhere, a world that once had stable conditions is being slowly, steadily, irrevocably consumed by its own dying sun. The most unsettling part of all this is that we already know it will happen here. The Sun is not exempt. It's a perfectly ordinary star following a perfectly ordinary life cycle. In about 5 billion years, it will leave the main sequence. It will swell into a red giant. And the inner solar system, the region where Mercury, Venus, and Earth orbit today, will be transformed beyond recognition. But knowing that a star expands and brightens is only part of the story. What really matters is what this transformation does to the planets nearby. Because the destruction of a planet by a dying star is not a single event. It's a cascade of catastrophes. each one more severe than the last, and it begins long before the star ever physically touches the planet. Now that you understand what happens inside a dying star, let's turn our attention outward. Let's look at what that transformation does to the worlds orbiting nearby. Because the death of a star is not just a story about the star, it's a story about everything around it. Every planet, every moon, every asteroid caught in the star's gravitational embrace experiences the consequences of that stellar transformation. And for planets orbiting close in, the consequences are devastating long before the star ever physically reaches them. The destruction begins with light. That might sound strange. Light seems harmless. You feel it on your face when you step outside on a sunny afternoon. You need it to see. Plants need it to grow. Light is life. But light, when there's enough of it, is also death. And when a star leaves the main sequence and begins to swell into a red giant, the amount of light it produces doesn't just increase a little. It increases by factors of hundreds, then thousands. A star like the Sun in its current state produces a certain amount of energy every second. That energy output is called its luminosity. Right now, the Sun's luminosity is remarkably steady. It's the luminosity that Earth has adapted to over billions of years. Our oceans, our atmosphere, our climate, our entire biosphere is calibrated to this particular amount of incoming energy. Everything works because the energy arriving from the Sun is within a range that allows liquid water to exist on the surface. But as the Sun evolves off the main sequence, as it begins its transformation into a red giant, its luminosity climbs. At first, the increase is gradual. Over the next billion years or so, the Sun will brighten by roughly another 10% above its current output. That doesn't sound catastrophic, but even that modest increase will have serious consequences for Earth. Climate models suggest that within about 1 billion years, the Sun's increasing brightness will push Earth's surface temperatures high enough to begin evaporating the oceans. Not all at once, but steadily. The added energy will accelerate the water cycle, putting more water vapor into the atmosphere. Water vapor is itself a greenhouse gas, which traps more heat, which evaporates more water, which traps more heat. It's a runaway feedback loop. Eventually, Earth's oceans will boil away entirely, and the planet will enter a state similar to what Venus is today. A hot, dry, suffocating world with a thick atmosphere trapping enormous amounts of heat near the surface. And that's just from a 10% increase in luminosity. That's the gentle part, the quiet prologue before the real transformation begins. But the truth is even more sobering than that, because Earth's death as a habitable world doesn't begin with the oceans visibly boiling. It begins far more quietly, through a process that most people have never heard of, the moist greenhouse. Here's the distinction, and it matters. A runaway greenhouse is the dramatic end stage, the point where the oceans are actively boiling, the surface temperature is climbing without limit, and the planet is transitioning into a Venus-like hellscape. That's the catastrophe everyone pictures. But before you get there, long before the oceans start boiling, the atmosphere enters a different state called the moist greenhouse. In a moist greenhouse, the surface temperature hasn't yet reached the boiling point of water. The oceans are still liquid. From the ground, the planet might even look roughly normal. But the upper atmosphere has changed in a critical way. Water vapor, which normally stays concentrated in the lower atmosphere because it condenses and falls back as rain, begins to saturate the upper atmosphere in quantities far higher than normal. The stratosphere becomes wet. This matters enormously because of what happens to water molecules in the upper atmosphere. Up there, above the protective blanket of the lower atmosphere, water molecules are exposed to intense ultraviolet radiation from the star. That radiation breaks them apart. The oxygen atoms are heavy enough to stay bound to the planet, but the hydrogen atoms are light. Incredibly light. Light enough to reach escape velocity and drift off into space permanently. This is called hydrogen escape, and it's how a planet can lose its water without ever visibly boiling it. The water doesn't disappear from the surface all at once. It evaporates normally, rises into the upper atmosphere, gets split apart by ultraviolet light, and the hydrogen leaks away into the void atom by atom. The oxygen left behind reacts with surface rocks or other atmospheric gases. Over hundreds of millions of years, the oceans shrink, not because they're boiling, but because their water is being disassembled in the upper atmosphere and the pieces are being lost to space. The moist greenhouse is insidious precisely because it's invisible from the surface. If you were standing on Earth during this phase, the sky would look blue, rain would fall, the oceans would stretch to the horizon. But high above you, water molecules would be quietly splitting apart and their hydrogen drifting away into the darkness. The planet would be slowly drying out from the top down. Climate scientists estimate that Earth could enter the moist greenhouse state within roughly 1 billion to 1.5 billion years as the sun continues to brighten. The runaway greenhouse, the dramatic boiling stage, might not occur for another billion years after that, but by the time the oceans visibly boil, much of the water will already be gone, lost molecule by molecule through the upper atmosphere over the preceding hundreds of millions of years. The moist greenhouse is the quiet prelude. The runaway greenhouse is the final act. But the planet is doomed long before the curtain falls. This distinction matters because it sets the true deadline for habitability. Earth doesn't have 5 billion years of comfortable conditions remaining. It has roughly 1 billion, maybe 1.5 billion, if conditions are favourable. After that, even if the surface temperature hasn't yet reached boiling, the oceans will be shrinking, the atmosphere will be changing, and the conditions that support complex life will be deteriorating. We are not at the beginning of Earth's habitable lifespan. We're in the final quarter. As the sun continues to evolve over the following several billion years, the luminosity climbs much more steeply. By the time it reaches the tip of the red giant branch, the sun will be roughly 2,000 to 3,000 times more luminous than it is today. Try to comprehend what that means for the inner solar system. Earth currently receives a certain amount of solar energy per square meter of its surface. Multiply that by 2,000. Multiply it by 3,000. The energy flooding into the space where Earth orbits will be thousands of times greater than anything the planet has ever experienced in its entire 4.5 billion year history. At these luminosities, there is no atmosphere that can survive on a rocky planet at Earth's current distance. There is no ocean. There is no ice. There is no liquid of any kind. The surface of a planet bathed in that much radiation becomes a searing, molten hellscape. Rocks begin to soften. Metals that were stable for billions of years start to deform. The entire surface of the planet is reshaped by energy that was never supposed to reach these levels. But luminosity is only part of the assault. The type of radiation changes too. A main sequence star like the Sun emits most of its energy in the visible spectrum, the kind of light your eyes can detect. But as a star expands and its surface cools, the peak of its radiation shifts toward longer wavelengths, toward the red and infrared end of the spectrum. This means a red giant emits proportionally more infrared radiation, more heat, for a given amount of visible light. At the same time, the inner regions of the star, the hot layers beneath the surface, continue to produce significant amounts of ultraviolet radiation. The star's chromosphere and corona remain intensely hot even as the surface cools, and for close-in planets, this ultraviolet radiation is devastating. Ultraviolet light has enough energy to break apart molecules in a planet's atmosphere. It can split water molecules into hydrogen and oxygen. The lightweight hydrogen atoms, once freed, move fast enough to escape the planet's gravity entirely and drift off into space. This process is called photodissociation followed by atmospheric escape, and it's one of the most efficient ways to strip a planet of its water permanently. You don't need to boil the oceans thermally if you can disassemble the water molecules with radiation and let the hydrogen float away into the void. This is not speculation. We see evidence of this process happening in our own solar system right now. Mars lost most of its atmosphere over billions of years, partly because the solar wind and ultraviolet radiation from the sun slowly eroded it. Mars is smaller than Earth and lost its magnetic field early in its history, which left its atmosphere exposed and vulnerable. Without a magnetic shield, the charged particles in the solar wind interacted directly with the upper atmosphere, knocking molecules free and carrying them away into space. Over hundreds of millions of years, this slow erosion stripped Mars of most of its air and all of its surface water. Now, imagine that same process, but with a star that's thousands of times more luminous, producing vastly more ultraviolet radiation, and a stellar wind that's enormously more powerful. The erosion that took hundreds of millions of years on Mars would happen in a fraction of that time. A planet's atmosphere wouldn't slowly leak away over geological timescales. It would be blasted away, peeled back layer by layer in what amounts to a cosmic sandblasting. Let's talk about stellar wind, because this is one of the most underappreciated aspects of stellar death. Right now, the sun produces a solar wind, a continuous stream of charged particles, mostly protons and electrons, flowing outward from its surface in all directions at speeds of roughly 300 to 800 kilometers per second. This wind is relatively gentle by stellar standards. It carries away only a tiny fraction of the sun's mass each year, roughly 2 to 3 million tons per second. That sounds like a lot, but compared to the sun's total mass of about 2 billion tons, it's negligible. The sun could sustain this wind for trillions of years without losing a meaningful fraction of its mass. But when a star becomes a red giant, the stellar wind intensifies dramatically. The mass loss rate increases by a factor of roughly 100 million compared to the main sequence wind. Instead of losing a few million tons per second, a red giant can lose mass at a rate equivalent to an entire Earth mass every few thousand years. The wind speed may actually decrease because the star's bloated envelope has a weaker gravitational hold on the outflowing material, but the density of the wind increases enormously. There are far more particles streaming outward per unit volume of space. For a planet caught in this wind, the effect is relentless. The wind slams into the planet's upper atmosphere, transferring energy and momentum to atmospheric particles. It pushes against the magnetic field, if the planet has one, compressing it on the star-facing side and stretching it out into a long tail on the far side. If the planet's magnetic field is strong enough, it can deflect most of the wind around it, protecting the atmosphere underneath. Earth's magnetic field does this today. It channels the solar wind around the planet, creating a protective bubble called the magnetosphere. But there are limits to what a magnetic field can withstand. A stellar wind that's millions of times more intense than the current solar wind can overwhelm even a strong magnetic field. The wind compresses the magnetosphere, pushing it closer and closer to the planet's surface. Eventually, the magnetosphere may be pushed so close that it can no longer shield the upper atmosphere effectively. The wind begins to interact directly with atmospheric particles, stripping them away and carrying them off into space. And if the planet doesn't have a magnetic field, which is the case for many rocky planets, the atmosphere has no defense at all. The wind hits the upper atmosphere directly and begins eroding it from day one. Consider what this means for a planet like Earth. Earth has a relatively strong magnetic field generated by convection currents in its liquid iron core. This field has protected our atmosphere for billions of years. But Earth's magnetic field is not infinitely strong. In the face of a red giant stellar wind millions of times more powerful than the current solar wind, Earth's magnetosphere would be severely compressed. The protection it provides would be degraded. And over millions of years of exposure to this intensified wind, even a magnetically shielded planet would lose significant amounts of its atmosphere. For a planet without a magnetic field, the situation is far worse. Venus, for example, has no global magnetic field. Today, the solar wind interacts directly with Venus's upper atmosphere. The solar wind strips away atmospheric particles, mostly hydrogen and helium, at a measurable rate. Venus retains its thick atmosphere despite this erosion, because the current solar wind is relatively mild, and Venus's atmosphere is massive. But scale up the stellar wind by a factor of millions, and the equation changes completely. Even a thick atmosphere like that of Venus would be eroded at a catastrophic rate. Over millions of years, a planet in the inner solar system could lose its entire atmosphere to the intensified stellar wind of a red giant. Now, let's combine all of these effects because they don't happen in isolation. They happen simultaneously. A planet orbiting close to a star that's leaving the main sequence is hit by multiple overlapping catastrophes at once. First, the luminosity increases. The planet receives vastly more energy. Its surface temperature rises dramatically. Any liquid water on the surface begins to evaporate. The atmosphere heats up, expanding and becoming less tightly bound to the planet by gravity. Second, the increased ultraviolet radiation breaks apart atmospheric molecules. Water is split into hydrogen and oxygen. The lightweight hydrogen escapes into space. The planet is being chemically disassembled from the top down. Third, the intensified stellar wind hammers the upper atmosphere, physically stripping away particles and eroding whatever the ultraviolet radiation hasn't already destroyed. The magnetic field, if there is one, is compressed and weakened, reducing its protective effect. Fourth, as the atmosphere thins, any remaining volatile compounds on the surface, ices, organic molecules, anything with a relatively low boiling point, are vaporized and either broken apart by radiation or swept away by the wind. The planet is being dismantled piece by piece, and the process accelerates over time because each stage makes the planet more vulnerable to the next stage. Losing atmosphere reduces the planet's ability to retain heat through the greenhouse effect, but it also reduces the atmosphere's ability to shield the surface from radiation. As the surface becomes more exposed, more material is vaporized, adding to the atmospheric loss. It's a cascade of destruction where each step feeds into the next. It's worth noting that not all planets experience this cascade the same way. The composition of a planet's atmosphere dramatically affects how it responds to increasing stellar radiation. Earth has a relatively thin atmosphere dominated by nitrogen and oxygen, with trace amounts of carbon dioxide and water vapor. This atmosphere is vulnerable in specific ways. The water vapor amplifies heating through the greenhouse effect. The nitrogen and oxygen can be stripped by stellar wind once the magnetic shield fails. The atmosphere is thin enough that once erosion begins in earnest, it can be removed entirely within a geologically short time frame. But consider a sub-Neptune, a type of planet discovered in enormous numbers around other stars. These worlds have thick hydrogen and helium envelopes surrounding a rocky or icy core, atmospheres weighing hundreds or even thousands of times as much as Earth's. For such a planet, the early stages of stellar evolution are less immediately threatening. The increased luminosity heats the upper atmosphere, and the stellar wind begins eroding it. But there's so much atmosphere to erode that the process takes far longer. The planet can absorb punishment that would strip a planet like Earth bare, simply because there's so much more material to work through. However, hydrogen-dominated atmospheres have their own vulnerability. Hydrogen is the lightest element. It escapes from a planet's gravity far more easily than heavier gases like nitrogen or oxygen. As the star brightens and the upper atmosphere heats up, hydrogen atoms gain enough energy to escape in enormous quantities. A sub-Neptune exposed to increasing stellar radiation can lose its entire hydrogen envelope over hundreds of millions of years, a process astronomers call photoevaporation. What remains after the hydrogen is gone is the stripped core, a bare rocky or icy world with no atmosphere at all. Astronomers believe this process has already sculpted the population of exoplanets we observe. There's a notable gap in the size distribution of exoplanets, a scarcity of planets between roughly 1.5 and 2 times Earth's radius. This gap, called the radius valley, is thought to be caused by photoevaporation. Planets slightly larger than Earth lost their hydrogen envelopes and shrank, while planets much larger than Earth retained theirs. The radius valley marks the dividing line between survival and atmospheric loss. A planet with a thick carbon dioxide atmosphere, like Venus, responds differently again. Carbon dioxide is a heavy molecule, much harder to strip than hydrogen and more resistant to photodissociation. A Venus-like planet might retain its carbon dioxide atmosphere long after its water has been destroyed, ending up scorchingly hot with a thick, suffocating blanket of carbon dioxide but no water at all. It survives in the sense that it retains an atmosphere, but the conditions are about as far from habitable as you can get. These differences matter because stellar evolution doesn't affect all planets equally. Even at the same distance from the same star, a sub-Neptune, an Earth-like world, and a Venus-like world would follow different paths toward uninhabitability. The end result might be the same, but the journey would be different for each one. Let's apply this to our own solar system because it's the example we understand best, and it paints a vivid and sobering picture. Mercury is already a world with essentially no atmosphere, orbiting at about 36 million miles from the Sun, with surface temperatures swinging from roughly 800 degrees Fahrenheit on the sunlit side to minus 290 degrees on the dark side. It has no magnetic field strong enough to protect an atmosphere. When the sun begins to expand, Mercury will be the first planet affected. As the sun's luminosity climbs, Mercury's surface temperature will rise far beyond its current extremes. Long before the sun physically reaches Mercury's orbit, the planet will be baked to temperatures that can melt most metals. Its surface will soften, deform, and eventually begin to flow. Mercury will become a molten ball of rock and metal, slowly losing mass as material is vaporized from its surface and carried away by the stellar wind. By the time the sun's outer envelope actually engulfs Mercury's orbit, the planet may already be substantially eroded, a diminished remnant of its former self being swallowed by a wall of stellar gas. Venus is next. Venus already has a surface temperature of roughly 900 degrees Fahrenheit, maintained by an extreme greenhouse effect driven by its thick carbon dioxide atmosphere. Venus is a cautionary example of what happens when atmospheric heating runs out of control. But even Venus, as hot as it already is, will be transformed by the dying sun. As the sun's luminosity climbs to tens, then hundreds, then thousands of times its current value, Venus will receive correspondingly more energy. Its already extreme surface temperature will climb higher and higher. The thick carbon dioxide atmosphere that currently traps heat so efficiently will itself begin to be eroded. The intensified stellar wind and ultraviolet radiation will strip the upper atmosphere, slowly thinning it over millions of years. Eventually, even Venus's massive atmosphere will be significantly depleted. The surface will be heated to temperatures that melt the crust. Venus will become a world of liquid rock, glowing faintly red beneath the enormous swollen star that fills most of its sky. And then there's Earth. Our planet sits about 93 million miles from the sun. Right now, that distance places us comfortably in the habitable zone, the region around a star where conditions allow liquid water to exist on a planet's surface. Earth's position in the habitable zone is the fundamental reason we exist. It's why our planet has oceans, a moderate climate, and the conditions necessary for life. But the habitable zone is not fixed. It's defined by the star's luminosity. As the star brightens, the habitable zone moves outward, and the region that was once perfect for liquid water becomes too hot. The inner edge sweeps past the planet, leaving it in what you might call the kill zone. For Earth, this process begins disturbingly soon by cosmic standards. Within roughly 1 billion years, the sun's gradually increasing luminosity will push Earth's surface temperatures past the threshold where the oceans can remain stable. The process will be gradual at first. Evaporation rates will increase, more water vapor will enter the atmosphere, amplifying the greenhouse effect. Global temperatures will climb decade after decade, century after century, millennium after millennium, with no reversal. Eventually, the oceans will enter a state of runaway evaporation. Once the average surface temperature crosses a critical threshold, roughly around 140 degrees Fahrenheit by some estimates, the process becomes self-sustaining. More water evaporates, which traps more heat, which evaporates more water. The feedback loop runs to completion. The oceans boil away entirely. The water vapor rises to the upper atmosphere, where ultraviolet radiation splits it into hydrogen and oxygen. The hydrogen escapes into space forever. The oxygen reacts with surface rocks or is slowly lost to the stellar wind. In the span of a few 100 million years, Earth transitions from a blue, ocean-covered world to a dry, desiccated planet with a thick, stifling atmosphere of water vapor and carbon dioxide. The conditions become similar to Venus today, except the process doesn't stop there. The sun keeps brightening. Earth's situation keeps getting worse. By the time the sun reaches the red giant phase, billions of years later, Earth will have been a dead, sterile world for a very long time. Any life that once existed will be a distant memory, written only in the chemistry of irradiated rocks. What makes all of this especially haunting is the timescale. From a human perspective, these changes are unimaginably slow. 1 billion years is so far beyond a human lifetime that it's almost meaningless as a lived experience. You will never notice the sun getting brighter. Your grandchildren won't notice. 1,000 generations of your descendants won't notice. The change is too slow for any human timescale to detect. But from a planetary perspective, from the perspective of Earth as a geological entity, 1 billion years is not that long. Earth has already existed for 4.5 billion years. Life has existed for roughly 3.8 billion years. Complex multicellular life has existed for about 600 million years. The sun's increasing luminosity will make Earth uninhabitable within about 1 billion years. That means Earth is already past the midpoint of its habitable lifespan. We're not at the beginning of the story, we're closer to the end. Most of Earth's time as a living, ocean-bearing world has already passed. This realization carries weight beyond academic interest. It means that Earth's current state, its oceans, its atmosphere, its rich and diverse biosphere, is not permanent. It's a phase. A long phase, but a phase nonetheless. Earth was not always like this. 4 billion years ago, it was a molten world bombarded by asteroids. And it will not remain like this. Eventually, the sun's evolution will reclaim the conditions that made life possible here. The oceans will vanish. The atmosphere will be stripped. The surface will be sterilized by heat and radiation. And it's not just our solar system. Every planetary system in the universe with a sun-like star faces the same reckoning. Every planet that formed in a habitable zone around a main sequence star is living on borrowed time. The star that gave it life will eventually take that life away. Not out of malice, not out of intention. Simply because stars evolve. They change. They leave the main sequence and become something different. Something vastly larger and more luminous and more destructive. Consider the exoplanets we've discovered. Many of the thousands of confirmed exoplanets orbit stars that are older than the sun. Some of these stars are already approaching the end of their main sequence lives. The planets orbiting those stars are already beginning to experience what Earth will experience in 1 billion years. A slow, inexorable increase in stellar radiation that will ultimately destroy any habitable conditions they might have had. We've even found planets that appear to be actively suffering the consequences of stellar evolution. The exoplanet HD 209458bz was one of the first exoplanets where astronomers directly detected atmospheric escape. Observations showed that the planet's atmosphere is being blown away by intense radiation from its host star, creating a comet-like tail of gas trailing behind the planet as it orbits. This planet is a hot Jupiter orbiting extremely close to its star, so the conditions are more extreme than what Earth will face. But the physics is the same. Radiation and stellar wind stripping away a planet's atmosphere, molecule by molecule. Another example is WASP-12b, a gas giant orbiting so close to its host star that it completes an orbit in just over 1 Earth day. Observations suggest This planet is being tidally distorted into an egg shape and is actively losing mass to the star. Material is being pulled from the planet's atmosphere and accreted onto the star. The planet is being consumed while we watch. Astronomers estimate that WASP 12b may be completely destroyed within about 10 million years. That's a blink of an eye in cosmic terms. Then there's Kepler 91b, a gas giant orbiting a red giant star. This planet orbits at a distance that would have been perfectly safe when the star was on the main sequence. But the star has expanded, and now the planet is dangerously close to the stellar surface. It's being bombarded by intense radiation and is likely experiencing severe atmospheric erosion. This planet is living through exactly the scenario we've been describing tonight. A world that once orbited safely, now being slowly destroyed by its own star's transformation. These examples remind us that what we're discussing is not hypothetical. It's not a thought experiment or a scenario confined to computer models. It's happening right now, across the galaxy, to real planets orbiting real stars. The physics of stellar evolution is playing out on worlds we can observe, and the consequences for those worlds are exactly what the models predict. Atmospheres stripped, surfaces scorched, planets distorted, eroded, and eventually consumed. The light that once gave a planet life becomes the very force that takes it away. The radiation that warmed oceans and powered photosynthesis becomes the radiation that boils oceans and shreds atmospheres. The star that was a planet's greatest ally becomes its executioner, and there is no defense. There is no technology a civilization could build to stop a star from evolving. There is no shield large enough to block the output of a red giant, thousands of times more luminous than the sun. The only escape is distance. Moving farther from the star, either by migrating to outer planets or leaving the system entirely. But for the planets themselves, for the rocks and metals and atmospheres that make up a world, there is no escape. They remain in their orbits, bound by gravity, receiving whatever the star sends them. And as the star dies, what it sends becomes lethal. We've now seen what radiation and stellar wind can do to a planet. We've seen how atmospheres are stripped, oceans are boiled, and surfaces are scorched by a star that's leaving the main sequence. But there's another force at work in this process. One that's even more dramatic in its consequences. Gravity. The same force that kept the planet safely in orbit for billions of years becomes the instrument of its final destruction. And that destruction takes a form that most people never think about. The planet doesn't just burn, it spirals inward and is consumed, swallowed whole by the bloated envelope of its own dying star. And that is where we'll go next. We've seen what radiation and stellar wind can do to a planet. We've watched atmospheres get stripped away, oceans boil into vapor, and surfaces scorch to the point where rock itself begins to flow. But all of that, as devastating as it is, represents only part of the destruction that awaits a planet orbiting too close to a dying star. Because there's another force at work here, a force even more fundamental than radiation. A force that has been quietly shaping the relationship between the star and the planet for billions of years. Gravity. Gravity is what holds a planet in orbit. It's the invisible tether connecting every world to its star. For billions of years, that tether keeps the planet moving in a stable, predictable path, circling the star at a safe distance, maintaining the delicate balance that allows oceans and atmospheres and potentially life to exist. But when a star begins to die, when it swells into a red giant, the nature of that gravitational relationship changes in ways that are deeply consequential. The same gravity that held the planet safely in orbit for eons becomes an instrument of destruction. Not because gravity itself changes, but because the geometry of the system changes dramatically. And in that new geometry, gravity does something it never did before. It begins to drag the planet inward, spiraling it closer and closer to the bloated star, until the planet is consumed. To understand how this works, you need to understand tidal forces. You're probably familiar with tides on Earth. The moon's gravity pulls slightly harder on the side of Earth facing it than the side facing away. That difference stretches the planet, creating the ocean tidal bulges you see every day. The same physics operates everywhere. Jupiter raises enormous tides on Io, driving intense volcanic activity across its entire surface. Tidal forces are not exotic or unusual. They're a natural consequence of gravity operating across an extended body. Anytime two objects are close enough for the gravitational pull to differ noticeably from one side to the other, tidal forces arise. And the strength of those tidal forces depends on two things: the mass of the object doing the pulling and the distance between the two objects. Increase the mass, and the tides get stronger. Decrease the distance, and the tides get much stronger. Tidal force increases with the inverse cube of the distance, which means halving the distance between two objects makes the tidal force 8 times stronger. This steep dependence on distance is what makes tidal forces so important when a star expands. When a star is on the main sequence, compact and relatively small, a planet orbiting at a comfortable distance experiences modest tidal forces from the star. The sun raises tides on Earth, but they're tiny compared to the lunar tides. The sun is much more massive than the moon, but it's also much farther away, and that distance reduces the tidal effect enormously. For a planet in a stable main sequence orbit, stellar tides are a minor footnote. They don't affect the planet's orbit in any meaningful way over billions of years. But when the star expands into a red giant, the situation changes dramatically. The star's mass doesn't increase. In fact, it loses mass through stellar winds, but the star's surface moves vastly closer to the planet. A star like the Sun will expand to a radius of roughly 1 astronomical unit, which means its surface will extend to approximately where Earth orbits today. For any planet whose orbit is smaller than the star's new radius, the star's surface is now right there, surrounding the planet, engulfing it. But even for planets orbiting slightly outside the expanded star, the fact that the star's mass distribution has changed, that so much of the star's material is now physically closer to the planet, means the tidal interaction between star and planet becomes enormously stronger than it was on the main sequence. This intensified tidal interaction has a critical consequence. It causes the planet's orbit to decay. Here's how it works. The star rotates, and the planet orbits. In most cases, the planet orbits faster than the bloated star rotates. Red giants rotate very slowly because as the star expanded, the same angular momentum was spread across a much larger volume. Think of an ice skater extending their arms. They slow down. The star has effectively extended its arms, and it spins much more slowly than it did on the main sequence. The planet, meanwhile, continues orbiting at a speed determined by its distance from the star's center of mass. For close-in planets, this orbital speed is much faster than the star's rotation rate. The planet is zipping around the star far more quickly than the star's envelope is spinning. Now, the planet's gravity raises a tidal bulge on the star. Just as the moon raises tidal bulges on Earth, the planet raises tidal bulges on the bloated star's envelope. But because the planet is orbiting faster than the star is rotating, the tidal bulge on the star doesn't point directly at the planet. Instead, it lags behind. The star's rotation carries the bulge, but the planet moves ahead of it. So the bulge sits slightly behind the planet along its orbit. This misalignment is crucial. The tidal bulge on the star has mass. That mass exerts a gravitational pull on the planet. And because the bulge is trailing behind the planet, its gravitational pull has a component that acts against the planet's direction of motion. It's like a gravitational brake, a subtle, persistent tug pulling backward on the planet, slowing it down fraction by fraction with every orbit. When you slow down an orbiting object, it doesn't just move more slowly in the same orbit. It drops to a lower orbit. This is a fundamental principle of orbital mechanics. An object that loses orbital energy falls inward. It spirals closer to the central body. And as it spirals closer, the tidal forces become even stronger because tidal force scales with the inverse cube of distance. Stronger tidal forces mean a larger tidal bulge, a stronger gravitational brake, faster orbital decay, and an even more rapid inward spiral. This is a runaway process. Once it begins, it accelerates. The planet spirals inward, the tidal forces grow, the decay rate increases, and the spiral tightens. The planet falls closer and closer to the star on a timescale that can be remarkably short by astronomical standards. Depending on the mass of the star, the mass of the planet, and the initial orbital distance, this tidal in spiral can play out over millions of years or even less. For the most extreme cases, where a massive planet orbits very close to a bloated red giant, the inspiral can happen in just tens of thousands of years. That's an eye blink in cosmic terms. A planet that orbited stably for billions of years can be dragged to its destruction in a geological instant. As the planet spirals inward, it eventually reaches the outermost layers of the expanded star. This is where the physics becomes extraordinary. The planet doesn't just crash into a solid surface. Stars don't have solid surfaces. The outer envelope of a red giant is an incredibly tenuous gas, far less dense than the air you're breathing right now. The density at the outer edge of a red giant's envelope can be lower than the best vacuum we can create in a laboratory on Earth. The planet enters this gas like a bullet entering fog. But even though the gas is thin, it's there. And the planet is moving through it at tremendous speed. As the planet plows through the star's outer envelope, it experiences aerodynamic drag. The gas pushes back against the planet's motion, slowing it down. And just as with a tidal braking, slowing down an orbiting object causes it to drop to a lower orbit. The drag pushes the planet deeper into the star's envelope, where the gas is denser, which increases the drag, which pushes the planet even deeper. This is engulfment. The planet has entered the star, not by falling straight in, but by spiraling inward through an increasingly dense medium, losing energy with every orbit, sinking deeper and deeper into the stellar interior. The process can take thousands of years from first contact with the outer envelope to final destruction. During this time, the planet is experiencing conditions that escalate rapidly. As the planet sinks deeper, the temperature of the surrounding gas rises. The outer envelope of a red giant might be only a few thousand degrees at the surface, but the temperature increases steeply with depth. A few solar radii below the surface, temperatures climb to tens of thousands of degrees. Deeper still, hundreds of thousands of degrees. The planet's surface, whatever remains of it after the radiation and wind erosion we discussed earlier, is now immersed in gas that's hotter than any furnace ever built on Earth. The pressure increases too. At the surface of a red giant, the gas pressure is negligible, but deeper inside, the weight of the overlying gas compresses the material below. The pressure rises with depth, eventually reaching levels that can crush rock, deform metal, and compress the planet's structure. The planet begins to lose mass rapidly. The intense heat vaporizes rock and metal, and this vaporized material is swept away by the surrounding stellar gas. The planet shrinks, dissolved like a sugar cube dropped into hot water, attacked from all sides, its structure breaking down until nothing solid remains. The timescale for this dissolution depends on the planet's size and composition. A rocky planet like Earth, with a mass of roughly 6 trillion kilograms, would be vaporized relatively quickly once it reached sufficiently hot and dense regions of the star's interior. Computer simulations suggest that a planet with Earth's mass could be completely destroyed within a few thousand years of entering the denser regions of the stellar envelope. A gas giant like Jupiter, with over 300 times Earth's mass, would last longer, perhaps tens of thousands of years. But the outcome is the same. The planet is consumed. Its matter is absorbed into the star. Every atom that once made up the planet, every element forged in the supernova that seeded the original gas cloud from which the solar system formed, is returned to the stellar furnace. There is something poetically circular about this. The iron, silicon, oxygen, and carbon that make up rocky planets were originally created inside earlier stars, scattered by explosions, collected into clouds, and assembled into planets. For billions of years, those elements existed as a world. Now, as the star dies, it reclaims them. The planet's matter is absorbed back into the star, eventually ejected into space when the star sheds its outer layers as a planetary nebula, perhaps to be incorporated into new stars and planets billions of years from now. But let's not romanticize it too much. For the planet, engulfment is annihilation. Everything that made it a world, its geology, its atmosphere, its history, is erased. If that planet ever harbored life, every trace of it is vaporized and dispersed into the star's envelope. No fossil remains, no chemical signatures, nothing survives the interior of a star. Now you might ask, is this just theory? Do we have any evidence that stars actually consume their planets? The answer is yes, and the evidence has been growing steadily over the past 2 decades. One of the most compelling lines of evidence comes from chemical anomalies in stars. Astronomers have found red giant stars whose atmospheres contain unusually high levels of lithium. Lithium is a fragile element. It's easily destroyed inside stars because the temperatures required to burn it are much lower than those required for hydrogen fusion. Most red giants have very little lithium in their atmospheres, because any lithium that existed has long since been consumed. But some red giants show lithium levels far above what models predict. One explanation is that these stars recently consumed a planet. Planets contain lithium in their rocky interiors. When a planet is engulfed and vaporized, its lithium is released into the star's envelope, temporarily enriching the stellar atmosphere. The lithium signal fades over time as mixing and nuclear reactions destroy it, but for a period after engulfment, the star shows elevated lithium levels that betray what happened. The star BD plus 48740 is one example. This is a red giant with anomalously high lithium abundance and other chemical peculiarities that are difficult to explain through normal stellar evolution. Astronomers have proposed that this star recently consumed a giant planet, and the chemical evidence supports this interpretation. Another line of evidence comes from planets in unusual orbits around evolved stars. The planet 8 UMIB, orbiting a red giant star also known by its traditional name, Bake-Do, has been particularly puzzling. This planet is a gas giant orbiting remarkably close to its bloated host star, so close that it should have been consumed by the star's expansion, and yet it appeared to still be there. Some astronomers propose that the planet had somehow survived engulfment, perhaps by orbiting in a region where the stellar envelope was thin enough that drag hadn't yet pulled it in. Others suggested the planet might be spiraling inward, and we're simply catching it in the act, before it's fully consumed. More recent studies have cast doubt on whether the planet actually exists at all, suggesting the observed signal might be caused by stellar oscillations rather than a planet. The very ambiguity of this case illustrates how complex and active this area of research is. But the most dramatic evidence came in 2023. Astronomers announced the detection of what appeared to be a star in the act of swallowing a planet. The event, catalogued as ZTF SLRN-2020 after the year it was first recorded, was detected by the Zwicky Transient Facility, a survey telescope that monitors the sky for changes in brightness. The team observed a star that brightened dramatically over a period of about 10 days, then gradually faded over several months. The brightening was consistent with a planet spiraling into a star and being engulfed. As the planet plunged deeper into the star's envelope, the energy released by its destruction caused the star to brighten. The gradual fading afterward corresponded to the star settling back to its normal state after digesting the planet. The energy released during the event was consistent with a planet of roughly 1 to 10 Jupiter masses being consumed. The light curve, the pattern of brightening and fading, matched theoretical predictions of what planetary engulfment should look like. This was the first time astronomers had directly observed a star consuming a planet in real time. It confirmed that planetary engulfment is not just a theoretical possibility. It happens, it's observable, and it's probably far more common than we realize, because most engulfment events would be easy to miss if you weren't watching the right star at the right time. Astronomers have also found indirect evidence by studying binary star systems, where two stars that should have nearly identical compositions show subtle differences, one having slightly more iron, silicon, or other rocky elements. The most natural explanation is that one star consumed planetary material, enriching its atmosphere. These chemical signatures persist for billions of years, providing a long-lived record of ancient planetary destruction. There's yet another piece of evidence we should consider. Astronomers studying the star Kepler-56, an evolved red giant, discovered two planets orbiting close to the star. Both planets are doomed. Their orbits are decaying due to tidal interactions with the expanded star, and models predict engulfment within roughly 130 million and 155 million years, respectively. They've survived this long because the star hasn't expanded quite far enough to consume them yet. But the tidal forces are already at work, slowly dragging them inward. We can measure their orbital decay. We can predict when they'll be consumed. It's like watching a slow-motion collision that won't complete for another 100 million years. The star V391 Pegasi C provides another fascinating case. This is a subdwarf star, a star that has already passed through the red giant phase and shed its outer layers. But astronomers discovered a planet orbiting it. This planet survived the red giant phase, probably because it orbited far enough out to avoid engulfment. But its orbit has been altered by the star's mass loss and evolutionary changes. It's a survivor, a world that watched its star transform and lived to tell the tale. Its existence tells us that not every planet is destroyed. Some, if they orbit far enough away, can survive the red giant phase and continue orbiting the remnant star. Let's talk about what engulfment does to the star itself, because the consequences aren't just one-sided. When a star consumes a planet, especially a large one like a gas giant, the star is affected too. The planet deposits energy into the star's envelope as it spirals inward. This energy input can cause the star to brighten temporarily, as we saw with ZTF SLRN-2020. The planet's angular momentum is also transferred to the star's envelope, which can spin up the star's outer layers. Some red giants that rotate faster than expected might owe their unusual spin to a past planetary engulfment. The planet wound the star up like a spring as it spiraled inward, transferring its orbital energy into the star's rotation. The chemical enrichment we discussed is another consequence. The planet's material, its rock, its metal, its ice, is mixed into the star's envelope. This can change the star's spectral signature, the pattern of light it emits, in subtle but detectable ways. Astronomers have developed techniques to look for these signatures, searching for stars that show chemical evidence of having consumed planetary material. In some cases, the planet's destruction might even trigger brief episodes of increased mass loss from the star. The energy deposited by the engulfed planet can heat the star's outer layers, causing them to expand and become even more loosely bound. This can enhance the stellar wind, causing the star to shed material at a faster rate for a period after engulfment. The planet's death ripples outward through the star, changing the star's behavior in ways that persist long after the planet itself has been completely dissolved. There's something profoundly unsettling about this picture. A planet orbits its star for billions of years. It's a stable, predictable relationship. The planet circles the star. The star provides light and heat. Everything is in balance, but the balance was never permanent. It was maintained by the star's fusion engine running on a finite fuel supply. When the fuel begins to run out, the balance tips. The star changes, the planet doesn't, and the mismatch between the changing star and the unchanging orbit creates a death trap. The planet can't move. It's locked in its orbit by the same gravity that's been holding it in place for billions of years. It can't back away from the star as the star expands toward it. It can't adjust its distance to maintain habitable conditions. It simply continues orbiting at the same distance while the star swells outward, eventually reaching it, enveloping it, and consuming it. For a planet with life, if such a planet exists around a star entering the red giant phase, the implications are staggering. The civilization on that planet, if one exists, would have millions of years of warning. They would see their star growing larger and brighter in their sky. They would measure the increase in temperatures, the rising seas, the change in atmosphere. They would know what was coming. The physics would be clear to them, just as it's clear to us. Their star is dying. Their world is doomed. The only question is what they do about it. Do they develop the technology to move to outer planets in their system? Worlds that are currently frozen, but will soon be warmed by the expanding star? Do they build spacecraft to travel to other star systems entirely? Do they find ways to survive that we can't even imagine from our current level of technology? Or do they simply watch, unable to escape, as their star slowly devours the world that gave them life? We don't know the answers to these questions. We don't even know if there are planets with civilizations facing this scenario right now, somewhere in the galaxy. But the physics tells us that this scenario is common. Every sun-like star will eventually become a red giant. Every close-in planet around such a star will eventually face destruction through some combination of the processes we've described: radiation stripping, atmospheric erosion, tidal and spiral, and ultimately, engulfment. It's a universal process. It happens everywhere stars have planets, and it has been happening for as long as stars have existed, roughly 13 billion years. The galaxy is filled with the ghosts of consumed planets, their atoms dispersed into stellar envelopes, and later scattered across interstellar space by planetary nebulae. Every red giant you can see in the night sky may have consumed one or more planets during its expansion. Every white dwarf you can detect may be the remnant of a star that once hosted worlds, now gone. The evidence of planetary destruction is woven throughout the galaxy, written in the chemistry of stars and the dynamics of surviving planetary systems. But not every planet meets this fate, and that's important. The outcome of stellar evolution for a nearby planet depends critically on the type of star and the planet's distance. Some planets survive, some are destroyed, some are transformed into something entirely new. Understanding what determines these different outcomes is what comes next. And it brings us to the final, crucial piece of this story: the question of who survives, who doesn't, and what's left behind when a star finally finishes dying. Not every planet meets the same end. That's one of the most important things to understand about this entire process. The story we've been telling, the slow expansion, the radiation assault, the tidal and spiral, the engulfment. That's the story of a planet orbiting close to a sun-like star. But the universe is filled with different kinds of stars. Stars come in an enormous range of masses, sizes, temperatures, and lifespans. And the type of star a planet orbits determines everything about how that planet's story ends. Some planets are consumed, some survive, some are transformed into something unrecognizable, and some are never threatened at all. Let's start at the extremes. The most massive stars in the universe, stars with 10, 20, 50, or even 100 times the mass of the Sun, live fast and die violently. These are the blue giants and supergiants, the brilliant luminous stars that dominate the night sky, not because they're close, but because they're so intrinsically bright that they can be seen across thousands of light years. Betelgeuse, the red supergiant in Orion, is one of these massive stars. It has roughly 15 to 20 times the mass of the Sun and is already in the final stages of its life. Stars like Betelgeuse don't fade gently. They explode. A star with more than about 8 times the mass of the Sun doesn't end its life as a white dwarf. It ends its life as a supernova, one of the most energetic events in the universe. When the core of a massive star exhausts its nuclear fuel, it collapses in on itself in a fraction of a second. The outer layers, no longer supported by the energy from the core, come crashing inward, hit the incompressibly dense collapsed core, and bounce outward in a titanic explosion. The energy released in a single supernova can briefly outshine an entire galaxy of hundreds of billions of stars. The explosion blasts the star's outer layers into space at speeds of tens of thousands of kilometers per second, creating an expanding cloud of debris that spreads across light years. For any planet orbiting close to a star that goes supernova, the consequences are absolute. There is no gradual spiral, no slow atmospheric erosion. The blast wave hits with a wall of energy and matter moving at a significant fraction of the speed of light. The planet is shattered, vaporized, reduced to plasma and scattered into the expanding debris cloud. Nothing survives, not planets, not moons, not asteroids. Even planets orbiting at great distances might not survive. The radiation pulse from a supernova, a burst of X-rays, gamma rays, and ultraviolet light, can sterilize the surface of a planet hundreds of astronomical units away. If the planet has an atmosphere, the radiation can strip it. If the planet has a magnetic field, the charged particle blast can overwhelm it. And the blast wave itself, though it weakens with distance, can still deliver enough kinetic energy to strip gas and loose material from a planet's surface, even at enormous distances. But here's the crucial difference between massive stars and sun-like stars. Massive stars live for only a few million to a few tens of millions of years. A star with 20 solar masses might burn through its fuel in 10 million years. That's an incredibly short time. Earth has existed for 4.5 billion years. These massive stars are born, live their entire lives, and explode in an interval that's less than 1% of Earth's current age. This means planets around massive stars never have time to develop in the way Earth did. They never have billions of years of stable conditions. They never have time for complex life to evolve, assuming life even has a chance to get started. The star burns through its fuel before anything significant can happen on the planet's surface. These stars are spectacular but brief, and their deaths are so violent that the question of planetary survival is essentially moot. Everything nearby is destroyed, and it happens before the planets have had time to develop into anything particularly interesting from a biological standpoint. Now let's go to the other extreme. The smallest stars in the universe are the red dwarfs, stars with masses between roughly 8% and about 50% of the Sun's mass. These are the most common stars in the galaxy. About 70% of all stars are red dwarfs. They're small, cool, dim, and incredibly long-lived. A red dwarf with about 10% of the Sun's mass can burn hydrogen for trillions of years. Not billions, trillions. The universe is only 13.8 billion years old. These stars have barely begun their lives. Not a single red dwarf in the entire observable universe has ever died of old age. Red dwarfs are interesting because many will never become red giants at all. The smallest are fully convective, meaning gas circulates throughout the entire star from core to surface and back. This ensures all the hydrogen, not just the core fraction that sun-like stars burn, is available as fuel, making them extraordinarily efficient. When these smallest red dwarfs do eventually exhaust their hydrogen, trillions of years from now, models suggest they won't swell into red giants the way sun-like stars do. Instead, they'll gradually transition into helium-white dwarfs, slowly cooling over enormous timescales without ever going through a dramatic expansion phase. Their planets, assuming they survive the star's other hazards like intense flare activity in the star's youth, could potentially orbit in relative safety for trillions of years. No expanding stellar envelope threatening to engulf them. No dramatic increase in luminosity driving runaway greenhouse effects. Just a slow, quiet, almost imperceptible fading over timescales that dwarf the current age of the universe. Slightly more massive red dwarfs, those closer to half the sun's mass, do eventually evolve off the main sequence and expand somewhat. But their expansion is far less dramatic than that of a sun-like star. They might swell to a few times their original size, not the 100-fold or 200-fold expansion that the sun will undergo. Planets orbiting in the habitable zones of these stars might experience significant heating and atmospheric stress, but they're far less likely to be physically engulfed. The red giant phase for these stars is shorter and less extreme, giving planets a better chance of surviving the transition. Though survival doesn't necessarily mean remaining habitable. So the type of star matters enormously. Massive stars kill their planets quickly and violently through supernova explosions. The smallest red dwarfs may never threaten their planets through expansion at all. It's the stars in between. The sun-like stars, with masses between roughly half and 8 times the sun's mass. That produce the scenario we've been exploring tonight. These are the stars that swell into red giants, expand to enormous sizes, increase their luminosity by factors of thousands, and threaten to engulf their inner planets through the combination of radiation, wind, tidal forces, and direct physical contact. Now, let's talk about what happens after the dying is over. Because for sun-like stars, the red giant phase is not the end of the story. It's the penultimate chapter. The final chapter is the white dwarf. After a sun-like star has exhausted its fuel, expanded into a red giant, shed its outer layers into a planetary nebula, and left behind an exposed core, what remains is a white dwarf. A white dwarf is an extraordinary object. It has roughly half the mass of the original star, compressed into a sphere about the size of Earth. The density is almost incomprehensible. A teaspoon of white dwarf material would weigh roughly 5 tons on Earth's surface. There's no fusion happening inside it, no energy generation. The white dwarf simply glows from its residual heat, slowly cooling over billions and eventually trillions of years. For any planets that survive the red giant phase, the white dwarf is their new star. And it's a profoundly different star from the one they knew. It's tiny, roughly Earth-sized, compared to the original star that was hundreds of thousands of miles across. It's hot at first, with surface temperatures that can exceed 180,000 degrees Fahrenheit immediately after formation. But it produces far less total energy than the original star did on the main sequence. A freshly formed white dwarf is luminous by white dwarf standards, but it's still only a fraction of a percent as luminous as the sun is today. Over time, that luminosity fades even further. A planet orbiting a white dwarf at the same distance where it once received comfortable warmth from a main sequence star now receives almost nothing. The planet freezes. Its atmosphere, if it still has one, might condense and fall to the surface as frost. Any remaining water freezes solid. The planet becomes a dark, frozen world orbiting a fading ember. The solar system after the sun becomes a white dwarf will look nothing like the solar system we know today. Mercury and Venus will almost certainly be consumed during the red giant phase. Earth's fate is uncertain, and we'll return to that in a moment, but Mars will probably survive. Jupiter, Saturn, Uranus, and Neptune, all orbiting at much greater distances, will almost certainly survive. However, they won't survive unchanged. During the red giant phase, the Sun will lose a significant fraction of its mass through stellar winds. Current models estimate the Sun will lose roughly 45 to 50% of its total mass before settling into its white dwarf state. This mass loss has profound gravitational consequences. A planet's orbit is determined by the star's mass. Reduce it by half and the gravitational pull weakens. Every surviving planet's orbit responds by expanding outward. Jupiter, currently orbiting at about 5 astronomical units from the Sun, might end up orbiting at roughly 10 astronomical units from the white dwarf. Saturn, Uranus, and Neptune will all drift outward proportionally. The outer solar system will spread out, becoming a more diffuse, more widely spaced collection of planets orbiting a tiny, fading star. The system will still be gravitationally bound, but it will be a colder, darker, emptier version of its former self. The surviving planets will also be changed. Jupiter and Saturn will have lost some of their atmospheric mass to the intense stellar wind and radiation during the red giant phase. Not enough to destroy them. These are massive worlds with deep gravitational wells, but enough to alter their upper atmospheres and possibly change their appearance. Their moons might be more severely affected. Moons with thin atmospheres or surface ices could lose significant material during the red giant phase. Europa's ice shell, for example, might partially sublimate. Titan's thick atmosphere might be substantially eroded. But the red giant phase brings something else to these outer moons, something unexpected: warmth. For billions of years, moons like Europa and Enceladus have been locked in the frigid outer solar system, far from the Sun's warmth, their surfaces crusted with ice. But when the Sun swells into a red giant, its luminosity increases by thousands of times. That flood of energy reaches even the outer solar system. Jupiter orbits at about 5 astronomical units. At the tip of the red giant branch, when the Sun is roughly 2,000 times more luminous than today, the energy arriving at Jupiter's distance would be equivalent to what Earth receives from the Sun right now. Think about what that means. Europa, a moon currently locked under a shell of ice, more than 10 miles thick, would suddenly be receiving Earth-like amounts of stellar energy. The surface ice would begin to melt. The subsurface ocean that we already suspect exists under Europa's ice could be exposed to the sky for the first time in billions of years. For a brief window of time, cosmically speaking, perhaps a few 100 million years, the moons of Jupiter and Saturn could experience conditions vaguely resembling habitable environments. Not exactly Earth-like. The radiation environment would still be harsh. The atmospheric conditions would be challenging, but liquid water on the surface is liquid water on the surface. It's the one ingredient we know life needs above all else. Saturn's moon Titan presents an even more dramatic transformation. Today, Titan has lakes and seas of liquid methane and ethane on its surface, with a thick nitrogen atmosphere and surface temperatures around minus 290 degrees Fahrenheit. When the red giant Sun floods the outer solar system with energy, Titan's methane lakes would evaporate. The surface temperature would climb dramatically. The thick nitrogen atmosphere would remain, heated to much higher temperatures. For a period, Titan might have conditions that allow liquid water to exist, though in a very alien environment. The chemistry would be complex and strange, nothing like Earth, but potentially interesting from a biological standpoint. These temporarily thawed moons represent one of the most fascinating aspects of stellar death. The habitable zone doesn't just move outward, it sweeps through the entire system, briefly warming worlds that were frozen for billions of years. It's as if the dying star, in its final act, gives the outer solar system a taste of the warmth it lavished on the inner planets for so long. The gift is temporary. Once the star sheds its outer layers and becomes a white dwarf, the warmth vanishes and the outer moons refreeze. But for a few 100 million years, these icy worlds experience a summer they never knew before. The mass lost during the red giant phase also destabilizes smaller bodies in the system. The asteroid belt between Mars and Jupiter, the Kuiper belt beyond Neptune, and the distant Oort cloud are all affected. As the Sun loses mass, its gravitational grip on these objects weakens. Orbital resonances that kept asteroids and comets in stable configurations for billions of years break down. Objects that were safely locked in place get nudged into new orbits. Some are flung outward, escaping the system entirely. Others are scattered inward, into the inner system, where they may collide with surviving planets or fall into the white dwarf. The solar system becomes gravitationally unsettled, a period of reorganization where the orbital architecture that held firm for billions of years is reshuffled. And then there's the planetary nebula itself. As the red giant sheds its outer layers, it creates an expanding shell of glowing gas that moves outward through the solar system at speeds of roughly 10 to 20 miles per second. If you were standing on the surface of a surviving outer planet when this shell passed by, the view would be unlike anything humans have ever witnessed. A luminous wall of gas glowing in reds and greens and blues from the excited atoms within it, expanding outward past you like a cosmic bubble. At the center of this expanding shell, the tiny white dwarf would glow with an intense blue-white light, its ultraviolet radiation illuminating the gas and making it fluoresce. It would be one of the most beautiful sights in the universe. And it would mark the end of the solar system as we knew it. The old star gone, the gas dispersing into interstellar space, the remaining planets settling into their new, wider orbits around the white dwarf remnant. A new, diminished, but still gravitationally bound system taking shape in the wake of the star's death. Now, one of the most fascinating areas of research in modern astronomy involves the study of what happens to planetary material around white dwarfs. Because even after the star has finished evolving, even after the drama of the red giant phase is over, the destruction of planetary material continues in a different form. Astronomers have discovered that a significant fraction of white dwarfs, perhaps 25 to 50%, show signs of heavy element pollution in their atmospheres. This is deeply puzzling if you think about it. White dwarfs have extremely strong surface gravity. Any heavy elements in their atmosphere, things like iron, silicon, calcium, magnesium, should sink below the surface within days to weeks, pulled down by the intense gravity. A white dwarf that formed millions of years ago should have a pristine atmosphere of pure hydrogen or helium with no trace of heavier elements. And yet, many white dwarfs show clear spectral signatures of heavy elements: iron, silicon, calcium, magnesium, oxygen, carbon. Sometimes even aluminum and nickel. These elements shouldn't be there. They should have sunk long ago. The only explanation is that these elements are being continuously supplied to the white dwarf's atmosphere by an ongoing external source. Something is falling onto the star, delivering rocky metallic material to the surface on a regular basis. That something is planetary debris, asteroids, comets, and fragments of planets that were broken apart by the white dwarf's tidal forces. Here's how it works. During the red giant phase, the star's expansion and subsequent mass loss destabilizes the orbits of small bodies in the system. Asteroids and comets that were in stable orbits for billions of years get gravitationally perturbed. Some are flung out of the system entirely, others are nudged into new orbits that bring them close to the white dwarf. And when a small body passes too close to a white dwarf, the tidal forces are extreme. White dwarfs are small but incredibly massive. The tidal gradient near a white dwarf's surface is enormous. A body that passes within the Roche limit, the distance where tidal forces exceed the body's own gravitational self-cohesion, is torn apart, shredded into fragments, pulverized into dust. This dust forms a disk around the white dwarf, a ring of debris much like Saturn's rings, but composed of pulverized rock and metal. Astronomers have detected these debris disks around several white dwarfs using infrared telescopes. The disks glow faintly in the infrared as they absorb and re-radiate the white dwarf's light. Over time, material from the disk spirals inward and accretes onto the white dwarf's surface, polluting its atmosphere with heavy elements. The white dwarf WD 1145 plus 017 is one of the most studied examples. Astronomers detected multiple chunks of rocky debris orbiting this white dwarf on extremely tight orbits, passing in front of the star and blocking a fraction of its light. The debris is actively disintegrating, trailing clouds of dust as it orbits. This is a planetary system in the process of being destroyed, not by stellar expansion, but by the tidal forces of the compact remnant left behind after the star's death. Another remarkable example is GD 362, a white dwarf whose atmosphere contains a staggering abundance of heavy elements. The composition of these elements closely matches what you would expect from a destroyed rocky body, similar in makeup to an asteroid or a terrestrial planet in our own solar system. The white dwarf has essentially eaten a world, and the chemical fingerprints of that meal are still visible in its atmosphere millions of years later. By analyzing the composition of polluted white dwarf atmospheres, astronomers can determine what the destroyed planetary material was made of. This is extraordinary. We're essentially performing archaeology on dead planetary systems, determining the composition of worlds that no longer exist by reading their chemical signatures in the atmosphere of the star that consumed them. It's as if the star kept a record of everything it ate, and by reading that record, we can learn about planets we'll never directly observe. The results have been remarkable. Many polluted white dwarfs show compositions consistent with rocky material similar to Earth's crust and mantle. Some show evidence of water-rich material, suggesting the destroyed body contained significant amounts of ice or hydrated minerals. A few show compositions that suggest differentiated bodies, objects large enough that their interiors had separated into a metallic core and a rocky mantle, like Earth. These weren't just random space rocks, they were substantial objects, possibly dwarf planets or larger, that were torn apart and fed to the white dwarf piece by piece. But here's something remarkable that complicates the picture of white dwarfs as purely dead and hostile environments. Astronomers have proposed that white dwarfs could host a second generation of habitable conditions. Not for the old planets that survived the red giant phase at great distances. Those are too far away to receive meaningful warmth from the tiny white dwarf. But for objects that migrate inward or are captured into very tight orbits close to the white dwarf itself, A white dwarf is small, roughly Earth-sized, but it's hot. A young white dwarf can have a surface temperature exceeding 100,000 degrees Fahrenheit. It radiates energy, just far less than a main sequence star. The habitable zone around a white dwarf, the distance where a planet could receive enough warmth for liquid water, is extremely close. Perhaps only 1 million miles from the white dwarf's surface. That's a tiny fraction of the distance between Earth and the Sun. Any planet in this zone would orbit incredibly fast, completing a full year in just a few hours. The concept sounds exotic, but astronomers have taken it seriously. A rocky body that migrated inward through gravitational interactions, or assembled from debris in the disk, could settle into this close habitable zone. The white dwarf would provide steady warmth for billions of years as it cooled, and the radiation environment, while challenging, would not necessarily be lethal with the protective atmosphere and magnetic field. In 2020, astronomers discovered a giant planet orbiting the white dwarf WD 1856 plus 534 in a remarkably tight orbit, completing a full revolution every 34 hours. This planet is far too massive and too close to be habitable itself, but its existence proved something crucial. Planets can survive in close orbits around white dwarfs. If a gas giant can do it, there's no physical reason a smaller rocky world couldn't end up in the narrow, habitable zone. The discovery remains a proof of concept, but it demonstrates that the idea of life after stellar death is not pure fantasy. The universe may offer second chances, even after the star that birthed a planetary system has died. This possibility adds a strange twist to the story. The same stellar death that destroys inner planets and scorches everything nearby might, billions of years later, create a new, diminished, but real opportunity for habitable conditions around the remnant. The star dies, the planets are destroyed or frozen, and then, slowly, a new arrangement emerges. A tiny hot star, a close orbiting rocky world, and just possibly conditions warm enough for liquid water. It would be a pale shadow of the original system. A single small world huddled close to a fading ember, catching the last warmth from a star that shone brilliantly billions of years ago. But it would be something. And in a universe where habitable conditions are rare and precious, something is meaningful. All of this brings us to the final question, the one that makes this entire story personal. What will happen to Earth? The Sun is currently about 4.5 billion years old. It's roughly halfway through its main sequence lifetime. In about 5 billion years, it will exhaust the hydrogen in its core and begin its transformation into a red giant. This is certain. The physics is well understood. The timeline is firmly established. The Sun will become a red giant. Over the following several 100 million years, the Sun will expand enormously. Its luminosity will increase by thousands of times. Its outer surface will balloon outward, consuming Mercury's orbit, then Venus's orbit. Both of these planets will be engulfed and destroyed, spiraling inward through the Sun's expanded envelope and being vaporized. Their atoms will become part of the Sun's outer layers, eventually to be expelled into space when the Sun sheds those layers as a planetary nebula. But Earth's fate is less certain, and that uncertainty is one of the most debated questions in stellar and planetary astrophysics. The Sun, at its maximum expansion as a red giant, will have a radius of roughly 1 astronomical unit. That's approximately the current distance from the Sun to Earth. Earth orbits right at the boundary of the danger zone. Whether Earth is consumed or barely survives depends on details that are still being refined in computational models. There are factors that could save Earth. As the Sun loses mass through stellar winds during its expansion, its gravitational pull weakens. Earth's orbit would expand outward in response, moving the planet farther from the Sun's center. If this orbital expansion happens fast enough, if Earth moves outward faster than the Sun's surface moves outward, then Earth could potentially stay just ahead of the expanding envelope. It would be a narrow escape, a world fleeing outward just fast enough to avoid being swallowed by the growing star behind it. But there are factors working against Earth too. Tidal interactions between the expanded Sun and Earth would act as a brake on Earth's orbit, as we described earlier. The tidal bulge on the Sun raised by Earth's gravity would lag behind Earth's orbital position, creating a gravitational drag that slows Earth down and causes it to spiral inward. This tidal drag works against the outward migration caused by mass loss. The question is, which effect wins? Does the outward push from mass loss exceed the inward pull from tidal drag? Or does tidal drag dominate, dragging Earth into the Sun's envelope despite the mass loss? Different research groups using different models have reached different conclusions. Some models suggest Earth will be engulfed, the tidal drag overwhelms the outward migration, and Earth spirals into the Sun's envelope during the tip of the red giant branch, when the Sun is at its maximum size. Other models suggest Earth will barely survive, ending up in a wider orbit around the white dwarf remnant, a scorched, airless, frozen world, but still intact. A study published in 2008 by astronomers Klaus-Peter Schroeder and Robert Conan Smith concluded that Earth would likely be engulfed, with tidal effects dominating over mass loss. Other researchers have challenged this, arguing the mass loss rate might be higher than assumed, pushing Earth outward more effectively. The honest answer is that we don't know for certain. The margin is thin. Earth sits right at the boundary between survival and destruction. A small change in these assumptions, the exact mass loss rate, the efficiency of tidal coupling between the Sun and Earth, the timing of the Sun's maximum expansion, can tip the result one way or the other. Earth's ultimate fate depends on details of solar physics that we haven't yet measured precisely enough to resolve the question. But even if Earth survives the engulfment, survival is a generous word. Long before the Sun reaches its maximum expansion, Earth will have been rendered completely uninhabitable. The oceans will have boiled away billions of years earlier. The atmosphere will have been stripped or transformed into a thick, suffocating blanket of steam and carbon dioxide. The surface will have been scorched to temperatures that melt rock. Any life that once existed will be long gone. The Earth that survives the red giant phase, if it survives at all, will bear no resemblance to the Earth we know. It will be a bare, blackened, airless sphere of rock and iron, orbiting a tiny white dwarf in the cold and dark. Mars will survive. It's far enough from the Sun that it will avoid engulfment entirely. But Mars will be even colder and more desolate than it is today. The white dwarf Sun will provide virtually no warmth at Mars's expanded orbital distance. Jupiter and the other outer planets will survive too, pushed outward by the Sun's mass loss, orbiting in the darkness around a fading stellar remnant. The outer solar system will persist as a collection of cold, dark worlds circling a dying ember, slowly cooling over trillions of years. This is the future of our solar system. Not a sudden catastrophe, but a long, slow transformation. The Sun that gave us life will eventually take it away, not out of malice, but simply because stars evolve. They change. They burn through their fuel and transform into something different. And when they transform, the planets around them must face the consequences. But there's something worth holding on to in all of this. The fact that we know this is coming. The fact that we can predict it, model it, understand the physics behind it. That's extraordinary. We're a species that arose on a small rocky planet orbiting a perfectly ordinary star. And through nothing but curiosity, observation, and mathematics, we've figured out not only how our star works, but how it will die, and what that death will mean for our world. We've looked 5 billion years into the future and seen what's coming. No other species on Earth has ever done this. No dinosaur ever looked up at the sun and understood that it would one day consume the inner planets. No trilobite ever calculated the rate of hydrogen fusion in the solar core. We did. And that knowledge, however sobering it might be, is a testament to what a small species on a small planet can accomplish when it decides to look up and ask questions about the universe. The stars are not eternal. The orbits we think of as permanent are only temporary. The stability we take for granted is a phase, not a final state. Every star that shines tonight will eventually die. And when it does, the planets that orbit it will face a reckoning. Some will be consumed. Some will survive as frozen relics. And some, like Earth, will sit right on the boundary, their fate uncertain, balanced on the knife edge between destruction and survival. That's the universe we live in. A universe where the very thing that creates the conditions for life eventually destroys those conditions. Where the star that warms your face today will one day incinerate the ground you're standing on. Where the only constant is change, and the only certainty is that nothing lasts forever. Not planets, not stars, not even the arrangements of matter that, for one brief and beautiful moment, became alive and looked up at the sky and wondered what it all meant. But perhaps that impermanence is what makes it all so precious. A sunset that lasted forever would stop being beautiful. A life that never ended would lose its urgency. The fact that Earth's habitability has an expiration date, that the sun's warmth will not last forever, doesn't diminish what we have right now. If anything, it sharpens it. Every ocean wave, every rainstorm, every sun rays over a living world, all of it is temporary. All of it exists within a window of time opened by the steady burning of a star that will one day change beyond recognition. We live in that window. We are part of that window. And the window will close. 5 billion years is a long time. Long enough that it shouldn't keep anyone awake at night. The sun will rise tomorrow, just as it has for 4.5 billion years. It will be steady, reliable, warm. The oceans will catch the light. The atmosphere will hold in the heat. Life will continue in all its complexity and beauty and strangeness. Nothing about the distant future diminishes the present. The sun gave us time, billions of years of time. Time enough for life to emerge from chemistry, for consciousness to arise from biology, for a species to evolve that could look up at the star keeping it alive and understand exactly how that star works, how it will die, and what that death will mean. That understanding is not a burden, it's a gift. It tells us where we stand, not at the center of anything, not permanent, not guaranteed, but alive, aware and capable of comprehending the very processes that will one day end everything we know. We look at the fire that warms us, and instead of turning away from the knowledge that it will someday go out, We study it. We measure it. We carry that understanding forward, building a picture of the cosmos that grows more honest with every passing century. Sleep well tonight, knowing that the sun will rise tomorrow, steady and reliable, just as it has for 4.5 billion years. That steadiness is real. It will last for another billion years at least, before the changes become consequential. A billion years is long enough for a species like ours to do extraordinary things, if we choose to. The sun gave us time. What we do with that time is up to us. Good night.